Good morning, class. The session is being recorded. So I ask you to make sure your audio video is completely muted. Don't put anything in the chat. If there is any issue that you're concerned with, please don't even put your name there. Put your initials, change them to your initials. I ask you to change them back when I stop the recording. Also, if I ask you a question, if I ask you to participate, please do not participate if you have an issue with privacy. So we are looking at section 3.5, the chain rule. We covered a few sections. Put that in slide mode. Derivatives and rates of change, derivatives as a function, basic differentiation formulas, the product and quotient rules. So of course, we have tons of formulas here. Everybody is hopefully familiar with them, from the basic rise over run, which is the good old slope, okay, the average rate of change of y with respect to x if we have 2 points given. And it becomes the slope of a secant line to the slope of a tangent line. The definition, okay, here's the definition of differentiation. Here's another definition. Then there were a lot of formulas we covered, okay, basic power rule, exponential rule, trigonometric functions, and we also looked at the product and a quotient rule, and we are adding the chain rule now. To understand the chain rule, we need to know what's a composite function, and f of g is f of g of x, which can be easily calculated, and that's different than g o f of x. And the reason we need the chain rule, so we can handle composite functions. We can use, simply put, the derivative of f of g or f of g of x is f prime of g of x times g prime of x. This is the shell function, this is the inner function, or we can use the Leibniz notation. dy dx is dy du times du dx. This is the good old power rule. The derivative of x to the power of n is n x to the power of n minus 1. The general power rule or the extended power rule, instead of x, we have a function of x, like g of x. In which case, the first part is the same, n sits in front. The second part, instead of x to the power of n minus 1, now we have g of x to the power of n minus 1. And then by the chain rule, we need the derivative of g of x, which is g prime. I gave you this example because I truly believe that is helping with understanding the concept. Understanding that the shell function is sine. So you need to differentiate sine, which becomes cosine. Okay. And of course, you need the argument for cosine. So cosine of the same thing, 2x, and then times 2. Okay. In this case, again, you're still dealing with sine. So sine gives you cosine of the same thing, x squared. And then by the chain rule times 2x. This one, you write it as, again, it's worth looking at it, sine x to the second power. So you're looking at this extended power rule. N, 2 sits in front, sine g of x or sine x to the power of 2 minus 1 or 1. And the derivative of sine is cosine. And if you, get comfortable with that, I think the topic becomes fairly easy. This was good enough and simple enough to do it by two different ways, and we did that. So with Leibniz notation, dy du, the derivative of this one is 5u to the power of 4, and du dx, 30x squared. Now all you have to do, replace the u with 10x cubed plus 2, and you're done. In this case, you are going to write the composite function and then differentiate. Okay, everybody? And the purpose of this to show, in some cases, it is simple enough both ways. You can go either way. Sometimes it's not as easy. In this case, you're looking at the extended power rule. 50 sits in front. You change the exponent to 49, and then by the chain rule, we need g prime, the derivative of the inside 20x, and the rest is algebra. In this case, if you rewrite that using your algebraic techniques, you repeat the process of using the extended power rule. And simplification is your algebraic techniques. In this case, the only difference is this 5 doesn't go away. It's a multiplier. It's a coefficient. It just remains. Just carry it. That's all. The rest is just basic extended power. And when you carry it, it just makes the final answer 5 times 4 times 3, which is 60. In the case of an exponential, the derivative is always itself. Okay, all of them, the answer is itself. But by the chain rule, this one needs 10. Okay, the derivative of that is 10. So you multiply by 10. By the chain rule, the derivative of t squared is 2t. You need that. And this one, it is easier if we rewrite this as e to the power of 2t, and then we move on. So again, is itself times the derivative of the exponent, which is 2. Okay. So exponential functions, always the derivative is itself, and then see if you need to tag along anything else. Over here, we are looking at a case that is using the combination of a product rule. So if you put a raised dot here, you're multiplying 5x by 3x minus 2 to the power of 4. So this piece is, let's say, the f function, and this is the g function. So f prime g plus g prime f. So you're using the product rule. However, when you use the product rule, f prime, this is 5 times g, but the g prime uses the extended power. That's why you are using the combination class. Combination of the chain rule and the product rule. This one, g, in order to find g prime, 4 sits in front, the same thing, the power of 3, and then times 3. And then, of course, times 5x. You're done. As far as calculus is concerned, now you have a couple of steps to finish the job algebraically, and I can't emphasize the importance of being able to do that fairly nice and easy. It's really not that difficult, everybody. Anytime you have a number in the numerator, if you have a fractional expression, can you do it by the quotient rule? Yes, but you shouldn't. You use your algebraic technique to rewrite it and use the extended power rule on that, everybody. Extended power rule. Okay, so that takes care of the business. And again, of course, don't forget there are algebraic techniques you gotta be concerned with. Okay, everybody. Okay. Here's the next one. Now, because the numerator is a function, so is the denominator, you better keep it intact and use the quotient rule. Which means you are going to use f prime g minus g prime f over g squared. Here's the f function. Here's the g function. So you use the quotient rule. So the derivative of the top is simply 1 times the bottom. Minus g prime uses the chain rule or the extended power rule. That's why you're combining the quotient rule with the chain rule. So this gives you 4 times 2x minus 1 cubed times 2, and then times the top over the bottom squared. And you're done again with calculus. The rest is your algebraic techniques to simplify this properly. It's fairly simple. Go through the process. This cancels out, goes away, and this changes to 5. Okay, and then you simplify the brackets and you are done, everybody. This was the last page we looked at. Again, the numerator is a number, so don't use a quotient rule. Rewrite it using your algebraic techniques. Go to extended power rule and finish the job. This is done. You just rewrite it accordingly, everybody. You must always rewrite accordingly. How about this one? Well, first and foremost, we use the chain rule or the extended power rule. 5 sits in front. Here's your g function. You raise it to the power of n minus 1, 5 minus 1 or 4. And this now, g prime of x, requires the quotient rule, f prime g minus g prime f over g squared. Let me again write that because you need to be very comfortable with that. So you need f prime g minus g prime f over g squared, which means 2 times x minus 8 minus 1 times the top over the bottom square. So I hope you see that. It's pretty simple, okay? And you're done. Again, with calculus, you are going to move on and finish this algebraically, which requires simplification of the numerator for the second or the last fraction into negative 19 and combining them accordingly and noticing that the denominator x minus 8 is the same as x minus 8. This one has exponent 4, this one has exponent 2. The two of them together give us exponent 6. And that's extremely important to notice. It is your algebraic technique. The last question of the page, we dealt with this. And again, if you recall, I said, the way you read it, it makes a difference. So if I come across a question like this, I read cosine and I stop. Cosine. Meaning, I need to differentiate cosine. That's my shell function, the outer piece. That's my main function. So cosine gives me negative sine. Negative sine of what? You have to write the argument. Whatever this one is, you have to write it. So negative sine of 3t to the power of. By the chain rule, we multiply by the derivative of this, which is 12 t cubed, and it sits in front, and we're done. Now we're going to move on, everybody. Okay. Let's continue. Let's look at the new stuff. All right. E to the power of 5t as I mentioned, anytime you're dealing with the exponential, the answer is itself, class. So if I'm differentiating this, I would write e to the power of 5t and then times 5, because the derivative of 5t is 5. And I'm going to put it in front. So I'm going to write y prime is itself. And then I'm going to multiply by 5, and the 5 sits in front. And you're done. Okay? It's that simple. If I'm looking at part B, I'm going to do the same thing. I'm going to just write the answer as e to the power of 10 x. So I just wrote the same thing. What is the derivative of tangent? Secant squared, and you're done. Now, you don't have to put the secant squared in front, because if you put this in front, this x before e can be confusing. So if you wrote it in front, that's fine. Put a raised dot in between. Okay, but this is good enough. For this one, I think it's pretty obvious, but the only change I want to make sure everybody can see this is the same as writing e to the power of 2/3 x. So I want you to see that. Therefore, the answer is itself, e to the power of 2/3 x, and then you need the 2/3 which sits in front, and you're done. Okay, very simple, everybody. What happens when the base is e? The process is obvious. The answer is itself, and then you multiply either by k if it's kx or by g prime if it's g of x. What if the base is no longer e? Then we use logarithmic properties to go to base e because we do know the derivative when the base is e. So take a look at what we do. This is algebra, and I'm going to remind you of a couple of formulas that you've seen. E to the power of ln x equals x. I hope everybody remembers that. Ln e to the power of x is x. The two of them together refer to the fact that exponential functions and logarithmic functions are inverse functions. Okay, everybody? So with that being the case, because we don't know what the derivative of b to the power of x is, we are going to write b as e to the power of ln b. Just look at the parentheses. This parenthesis is just b, everybody. This is the same as b, okay? And so ln b, what is ln b? ln b is a number. Remember, it's not missing. But when you write it as ln is precise, e to the power of ln beta. This we know how to differentiate. The derivative is itself, and remember, ln b times x is like k times x. So times k or times ln b. Okay, times k or times ln b. Now, this part, we take it back to b to the power of x, everybody. So we take it back to b to the power of x times ln b. What does it mean? It simply means if you're differentiating e to the power of x, the answer is e to the power of x. But if you're differentiating b to the power of x, it's b to the power of x times natural log of the base. Okay, so class, let's just the reason, one way to look at it, you can say times ln e here for this guy, ln e is 1, so times ln b. What if it's a function? Now, instead of x, if it's a function of x, then times the derivative of that function by the chain rule. So if it's b to the power of f of x, the answer is itself, times ln b by logarithmic properties, times f prime by the chain rule. Let's look at a couple of examples, see how this thing is going to play out. Okay. According to this, what is the derivative of exponential? First, you write itself, 3 to the power of x. So that's the first thing. Immediately, you are going to write y prime is itself times. Because the base is not e, times ln of that. And you're done. You don't write ln3 in front unless you put a raised dot in between, okay? Now, how about this one? We do exactly the same thing, step by step. First, we say it's a exponential function. The answer is 2 to the power of 7x. The base is e? No, the base is different, so we need the ln of the base. Is the exponent x? No, it's a function of x. So we need the derivative of this guy, which is 7. And now we do rewrite it as follows. We put these two in front in this way. Okay, everybody? We put them in front as follows. I hope it's clear to everybody. Okay, I hope it's pretty straightforward. We are going to look at some applications. After T weeks, the number of people using a new rapid transit was approximated by the following. N of t 60 squared plus 500t plus 8,000. At what rate was the use of the system changing with respect to time after 8 weeks? There is one point in time given, so the rate refers to instantaneous rate. That means differentiation. So n prime of t. Very simple. 12t plus 500. Replace the t with 8. Replace it with 8. We get 12 times 8 plus 500. They add up to 596. As far as the units class, if by any chance you have a difficult time finding the unit, just rewrite it as dn dt. Remember, it represents change. So change in numbers, so number of people. Change in time. Units of time happen to be weeks, so people per week. What does it mean? Okay, and that's important to know. 8 weeks. After 8 weeks, the number of people using this is increasing by this much. On week 8, the number of people using the transit is increasing. If this is positive, you write down increasing. If it's negative, you write down decreasing. Don't write the negative sign here. So it's increasing at a rate of 596 people per week. Okay, people per week. Okay. Here's another example. A bacterial colony is estimated to have a population of such. P of t is 24t plus 10 over t squared plus 1 million t hours after the introduction of a toxin. Okay. The first part is algebra. What is the population after 1 hour? Just plug in. By the way, if it's a number is given 1, 2, 5, how many hours you plug in? Or it may be that they say after the introduction and they don't give you a time, that means 0, okay? And don't forget this is in millions, okay? So just plug in 24 times 1 is 24 plus 10 is 34 divided by 2 is 17. And now why million bacteria? Because it's given in that format, okay? The next part is asking about the rate, and it's given in one point in time. So that means differentiate and plug in 1. Differentiate using the quotient rule. All right, let's do that. This becomes 24 times the bottom minus the bottom gives you 2t times the top over the bottom squared. In other words, I'm using everybody, I'm going to use f prime g minus G prime F over G squared, where the top is F, the bottom is G. So we are using the quotient rule class. Okay. All right. So let's quickly recap. The top gives you 24 times the bottom, minus the bottom gives you 2t times the top over the bottom squared. All we have to do is simplify the top. We are done with this as far as calculus is concerned. So we are going to distribute 24t squared plus 24 minus 48t squared minus 20t. And as far as the numerator is concerned, 24t squared, negative 48t squared, they add up to negative 24t squared. So this is p prime of t, and after 1 hour, just plug in 1, come up with the answer. So when we plug in 1 and evaluate this, we get negative 5. This is 1 squared is 1 times negative 24. This is negative 24 class. This is minus 20. This is plus 24. And this is 2 squared or 4. Negative 24 cancels out positive 24. Negative 20 over positive 4 gives us negative 5. Why million? Again, go back to this. Okay. So negative 5 million bacteria per hour. So what does it mean? It means 1 hour, okay, after the toxin is introduced, the population of bacteria is decreasing by this much. So the population is decreasing at the rate of 5 million bacteria per hour, 1 hour after the toxin is introduced. Okay, so that's the meaning of it, everybody. Okay, so I hope it's straightforward. Hope everybody's okay with that. Observations show that the length in millimeters from nose to tail of a Siberian tiger can be estimated by the function L equals 0.25 W to the power of 2.6, where W is the weight in kilograms. Furthermore, a young tiger's weight can be estimated in terms of its age, T in days, by a function W is 3 plus 0.21 T. So part A, how long is a tiger when it's 100 days old? It's algebra. There are two ways to do this class. We can find the composite function or just deal with it the way it is. I'm going to show you both ways because both of them are actually fairly simple. It's worth looking at it. But ultimately, you have to realize sometimes one is easier than the other, and you really have to learn both, okay? So the first part is very straightforward class. How long is a tiger after it's 100 days old? So T is 100. That's what it means. T is 100. So plug in here. Plug in here. That gives you the weight. So 100 times 0.21, it becomes 21. Plus 3 becomes 24. So you plug in and you get 24. What are the units? Kilograms. Okay. Kilograms. Okay. Now, this 24 you put it into the L function, replace the W with number 24 and use a calculator to calculate the length, okay, in millimeters. So let's plug in. And it gives you 969.369 millimeters. So this formula, 0.25 W to the power of 2.6 is used. But I'm reminding you that 1 meter is 100 centimeters. 1 centimeter is 10 millimeters. So this is 1,000 millimeters, meaning your answer is almost 1 meter, almost. And 1 meter is about 3 feet. At what rate is the length increasing when it is 100 days old? Using the Leibniz notation, here's how we come up with the answer. At what rate, okay, at what rate is the length increasing when it's 100? So we want dl dt. So we are going to write dl here and dt here because take a look at the length. Length is not a function of time. So what is it a function of? It's a function of w. So I need dw here. So I need dw here. Okay, everybody? That's how you come up with that. I highly recommend you write it in the manner that I did. And now it becomes fairly simple. Okay, we're going to find each one accordingly. So what is dl dw? Okay, that means this is a function of w. Differentiate this. 0.25 times 2.6 w to the power of 2.6 minus 1 or 1.6. So 0.25 times 2.6 w to the power of 1.6. What is dw dt? It so happened that it's that simple, class. It's just 0.21. Okay, so this part is the first part. Okay, and this is this one. Okay, class. We are going to multiply 0.25 and 2.6 and 0.21, the three numbers. We get 0.1365 w to the power 1.6. Now let's go back to the question. It says, at what rate is the length increasing when it is 100 days old? Okay, there are two ways to do this, class. Number one, you can change the w to 3 plus 0.21t and then plug in 100. Because if you want to find this as a function of time, you have to replace it. Okay. However, this may even be a function of t, okay? Since it's a simple evaluation, replace the t with 100. This doesn't have any t. If it did, you would. But it has a w. So after 100 days, what is the weight? You've already calculated it here. Take a look. We know when t is 100, w is 24. Plug in. And you're done, class. So what do? Replace the w with the 24 you found in part A. Sometimes this may even have a t. Or you could say this is not a function of t, and you want to replace the t1 with 100. It's the same thing. The second method is to find the composite function L is a function of W, so replace the W with what is the given, 3 plus 0.21t, so 0.25 times this function to the power of 2.6. Do that. Now, if you replace this t with 100, you get the same answer as you got here. You get the same answer. And now if you want to differentiate this, how do you differentiate this? This is the extended power rule, 0.25 times 2.6 times the same thing to the power of 1.6 times 0.21, right? So 0.25 is there, 2.6 sits in front. You use the same parentheses to the power of 1 less, that means 2.6 minus 1 is 1.6, and then the derivative of the inside by the chain rule is 0.21. You multiply this number and this number and this number, you put it in front. And now you replace the t with 100 and it gives you absolutely the same answer. Now, what it means is the length of a Siberian tiger is increasing at a rate of 22.0532 millimeters per day after it is 100 days old. Okay, that's the meaning of it. I hope everybody is comfortable with that. Let's look at a similar question, and again, you can do it both ways, but I want to stick with one. The amount of glass recycled is G of a P equals square root of 0.5 P squared plus 7, where P is the population in thousands. So pay attention that the population is in thousands. Okay, and this glass thing is in tons. So you want to pay attention to both units. So tons of glass, thousands of people. Tons of glass, thousands of people. And it is estimated that 10 years from now, the population of the community will be as such, 4.4 plus 0.1 t squared. How many tons of glass are expected to be recycled? 4 years. T equals 4, everybody. T equals 4. Okay. Well, you plug in the 4 in here and you evaluate. So when you plug in 4 squared is 16 times 0.1. 16 times 0.1 is 1.6. And now added to 4.4 gives you 6. And remember, this is the population in thousands. So 6,000 people. That's the reason you put 1,000. Okay. Why 1,000? Because, you know, it was mentioned here. We want to make sure we have it correct. Okay. How many tons of glass is now? Plug in 6 here. When we plug in 6, what happens? So this is something you should know quickly. 6 squared is 36. Half of that is 18. So 18 plus 7. So you're looking at the square root of 25. So square root of 25, the answer is 5. Okay. The next part is asking, find the rate at which the amount of glass is changing with respect to time 4 years from now. So we want find the rate at which the amount of glass dg dt, which is again dg. I'm going to put the dt here. Now, all I have to look for, what's in between? G is a function of t? No, it's a function of p, so I need dp. Okay, so dg dp. To find dg dp, I'm going to rewrite this as 0.5 p squared plus 7 to the power of 1/2. So we're going to differentiate this. So dg dp, 1/2 sits in front, the same thing. to the power of 1/2 minus 1 or negative 1/2 times the derivative of the inside. By now, I think everybody knows the derivative of 0.5 p squared. That means 0.5 times 2p or 1p. So that's that. What is dp dt? 0.1 times 2t. 0.1 times 2t or 0.2t. Okay. Now, the reason I'm writing this because you have a choice here. Replace this p with this, replace this p with this, and use the fact that t is 4, or don't replace it. Keep the p intact, keep the t intact. This t is, of course, t equals 4, and this p, we have already calculated the p when t equals 4 is 6, so replace it with 6. That makes it a lot easier, class. By the way, we have already calculated this part, class. 18 plus 7 square root. This part is really 25. And the square root of it is 5. So this really becomes 1/5. So let's plug in. So 1/2, 0.5, p is 6 squared. This is 7. Everything is there. Just replace the p with 6 and t with 4 and evaluate. Okay. Now, this one, we've already done that. So this thing becomes 25, everybody. So what you're looking at is 25 to the power of negative 1/2. So I want to evaluate this on the side for you and refresh your memory here. 25 to the power of negative 1/2 means 1 over 25 to the power of 1/2, which is square root of 25, which is 5. So that part is 1/5. So here's what you have, everybody. Take a look. You have 1/2, you have 1/5, you have 6, and 0.2 times 4 is 0.8. So take a look. 1/2, this one we showed is 1/5, this number is 6, this one is 0.2 times 4, 0.8, and just multiply. You get 0.48. What does it mean? First of all, the units, tons per year, units of glass per unit of time. Secondly, what does it mean? After 4 years, the amount of glass recycled is increasing at a rate of 0.48 tons per year.